Okay, now let's talk a little bit about the transportation model using LP format. So for transportation model, let's simply use the simple case, Executive Furniture Company case here as stated in the lecture notes. So in this case, there are three facilities, three plants manufacturing our products. And also we have to serve three markets. For each plant, it carries a constraint specified by its capacity. So for, like say, plant 1 in Des Moines, the capacity it can only produce up to 100 units. And also there are another group of constraints in dealing with the demand. So for each market, it requires we satisfy the demand at a certain amounts of units. So using a standard LP format, coming to the model here, first of all, our decision variables is to set x sub ij equals the amount to be shipped from plant I to market J, or to location J here. And then our objective function is simply to minimize the total shipping costs. C sub ij here is the unit shipping cost for shipping 1 unit of product from facility I to the market J. So okay, we already mentioned that there are two groups of constraints. One group is the constraints set by the capacities. So in our case here, we have three facilities. So there are three equations. So in which case we expand that to be x sub 11 plus x sub 12 plus x sub 13 should be less than or equal to 100. And for demand constraints, so which means x sub 11 plus x sub 21 plus x sub 31 should be larger than or equal to 300 units. And of course, do not forget the non-negativity constraint for each decision variables. After we specify this model, and we say in Excel, for transportation model, it's better for us to set also in the regular matrix format. So with the information given, we say first of all we have information in regard to the unit shipping cost. So we have plant 1. Of course, you can change to be the city names and simply put in a general format. So if we have to serve like 4 markets, simply extend this matrix. So let's using board here. Decision variables, or simply we can specify as shipment. So initially, we say we ship 0 from each plant to different markets. So let solver find the optimal solutions. So we say there are two groups of constraints for this simple regular transportation model. First group is the capacity constraints. So total shipped out from each plant, we take summation of each row here. We know they should be less than or equal to the capacity. So 100, 300, and 300. In total, this company can produce up to 700 units of the product. And also there's a demand. The demands from each different markets. That's another group of constraints. 300, 200, and 200 units. So all these are given, and we know that total ship into each market, simply we take the summation of each column. So which should be larger than or equal to the demand of each market. So let's put them into that format here. And then our target here, the objective here is to minimize the total shipping costs. This simply equals some product unit shipping costs and the amounts to be shipped, which are our decision variables. So after we specify the model in this format, we go to solver, so this is our objective function, the target cell here, to minimize the value in this cell. Then select minimize by changing our decision variables, the shipment decision variables. And then the constraints. First of all is that the total shipped out from each plant should be less than or equal to the corresponding capacity. Second group is the total amounts shipped into different markets should be larger than or equal to the demands in each market. And of course, do not forget to check the non-activity box here. And also, this is a linear format, so we simply choose simplex or linear programming methods here. So after we specify a model in solver, then click solve button. Then of course you can select the answer and the sensitivity reports. So the optimal solution here is to ship 100 units from plant 1 to market 1 to the first market, and then from the second facility we ship 200 units to the second market and 100 units to the third market. And of course For the manufacturing facility 3, we are shipping 200 to the first market and 100 units of the products to the third market, in which case we are minimizing the total shipping costs equals $3,900. And this is a typical case, and this example here is very simple. So, and also very often we have to deal with some kind of situation. Let's say there are kind of alternative situation here. In our case here, we have capacity in total equals 700 units, and also the total demands equals 700 units. This is a balancing case here. And also, very often, the demands in total is larger than the summation of the total capacity. Then you need to including additional decision variables, which we call the shortage for each market. So there was the example also posted online, which called the transport 1 case. In that case, we need to including additional decision variables. So let's say here you can simply insert another 3 decision variable. Stands for the shortage for each market. Then the total shipped into each market plus the shortage should equal to the total demands in that specific market. And our total costs should including not only the total shipping costs, also should including it should equals the total shipping costs plus the total penalty, the shortage costs. So please check that example for detailed information. And also another kind of expansion of our transportation model is what we call transshipment model, in which case we are not shipping our products directly from our manufacturing sites to the market. Instead, more realistically, we first ship our products from the plants to the warehouses, then from our distribution centers, then from different distribution centers we ship our products to the final market, to the destination, to satisfy demands in different markets. And in Excel also it's very straightforward to set up that. Here we simply change our decision variable. Should be there are 2 groups of decision variables. First group is that from different plants to different, you have to change that to be warehouse 1, warehouse 2, warehouse 3. Then there's another group of decision variables from warehouse 1 to market 1, market 2, market 3, and also from warehouse 2 to market 1, market 2, market 3. So also we are minimizing total shipping cost. That shipping cost, like using a standard LP model here, it should equal the summation of this shipping cost x sub I now equals, set it equals to be amounts to be shipped from plant I to warehouse J, then plus another summation, double summation of, let's say, CL sub LM multiplied by X sub LM or sub JM, which stands for from warehouse J to the market M. That's also very straightforward. So suppose let's come back to the example listed on the slides here. In our case here, so we have 2 plants and 2 warehouses. Then we have 3 destinations. So in which case, simply say our decision variables warehouse 1, warehouse 2. So also initially we set all these to be 0. So let's put more rows here. To be market 1, market 2, market 3. So there are corresponding shipping costs. So we say 4577. Let's represent simply put them into shape. So 624354. So the total shipping costs should equal some product from shipping the products from different plants to the warehouses plus some product of the shipping costs from warehouses to the final destination, different markets. And then the constraints, just pay attention, for each plant the constraints are the same. Shipped out, simply equals summation of the different variable in the same row here. They should be less than or equal to the capacity for each manufacturing plant. So in our case here, let's check the capacity for Toronto and Detroit are 800 and 700. And also there are demands. For each market. You know that for New York City it requires 450 units to be shipped in, and Philadelphia required 350 and St. Louis required 300. So all these informations are given. Total amounts shipped into different markets should be larger than or equal to the demands in the market. Then for each warehouse, please pay attention. There's additional constraints here, which will bring us minimize the total shipping costs. In our case here, if we say we try to avoid or we try to ignore the storage costs, in which case, then we simply set that the total shipped into each warehouse equals total shipped out. So then total shipped into each warehouse and total shipped out from each warehouse. The constraint that total shipped in for warehouse 1 should be set to be equal to the total amounts to be shipped out from warehouse 1 to 3 different markets. And of course, you can relax that to be the amounts here larger than or equal to the amount here. But generally speaking, if we try to ignore the storage cost, then we simply say these two values are equal. And if the storage cost kicks into picture, then we have to consider total costs to be minimized, which takes it equals the summation of total shipping cost plus the total storage cost. So let's first just set the storage cost to be 0. In our case here, we say the total amount shipped into each warehouse should equal to be total amounts shipped out. Okay, now let's come to the modeling case here. We open solver. So our target cell is this one here, total shipping costs, which we try to minimize it by changing first the amounts shipped from different plants to different warehouses. I'll put a comma here, then the second range of our decision variables. So the constraints, first of all, we know that the amount shipped out from each manufacturing place should be less than or equal to the capacity. And then second group is that total amounts shipped into different markets should be larger than or equal to the amount required for each market. And then for the transshipment points for the warehousings or for the distribution center constraint, we know that first of all, the amount shipped into warehouse 1 should equal, or you can say larger than or equal to the amounts shipped out. Again, for the warehouse 2. So after we specify all these constraints, then also make sure the non-activity conditions, these constraints are checked here. And we select simplex linear programming methods. After that, hit OK button. So we see now the optimal solution here is to produce and ship 650 units from the first facility to warehouse 1, and also produce and ship 450 units from the second facility to the second warehouse. Then from warehouse 1 we ship 350 to the second market and 300 units to the third market. Then the first market is satisfied, the demand is satisfied by the second warehouse. We ship all amounts shipped into the second warehouse. We use all the total 450 units, ship them to market 1 here. So which will bring us the minimized total shipping cost of $9,550.